Hello. So in this video, we're going to be introducing polynomials. In particular, in this particular video, I'm going to go through sort of the language of polynomials and sort of give an idea of the kinds of stuff that we're going to be doing as we move along here. So polynomials are one of the sort of oldest, most well-studied things in math. Believe it or not, the sort of quintessential thing, a lot of people think of when they think of like quadratics, the quadratic formula. Believe it or not, a quadratic formula in one form or another was actually in use in 2000 BC, so more than 4,000 years ago. So we've been sort of studying and learning about polynomials for a really long time. As a result of that, it means that we've figured a lot of stuff out, and moreover, since calculus wasn't sort of invented until, much later, only a few centuries back, the whole idea of sort of the whole thing about polynomials is that a lot of the tools that we have to deal with them predate calculus, meaning that a lot of it is stuff that we can do in pre-calculus. So of all the functions we're going to study, polynomials have the most sort of depth and richness to them in terms of the stuff that we're going to be discussing. Moreover, they're sort of the most natural function to think about, as we'll see soon. They're sort of just generalized counting in some way, which is one of the reasons why they were sort of studied so early. It was actually studied in a much more commercial context than a mathematical context for a long time. So we're going to be looking through a lot of stuff with polynomials, a lot of it specific to polynomials because they're so well studied, but a lot of it as sort of general things that we can do with functions, with most all functions, not quite all of them, that's what the universal properties were for, but most functions will fall into the, these techniques might work on. And polynomials are sort of the easiest example to then use. So factoring is an example of this. We have a lot of factoring techniques that are specific to polynomials, but we have some factoring techniques that aren't. And so they're sort of a good type of function to sort of toy with to show these different techniques. So in this video, I'm going to basically talk about all the terminology and develop all that. In the next video, which is sort of an introduction part 2, I'm going to go through the actual notation and sort of importantly the generalized notation. And as we move through polynomials, we're going to go through different aspects of them, like how their degree affects the extrema and curvature of the graph, as well as all the different factoring techniques and division of functions and such. So we'll be going through lots and lots of technique. This also means that sort of in contrast to the stuff that we just did, where it was very sort of conceptual and much more, or I should say much less concrete, polynomials are very, like the techniques that we're doing are very mechanically concrete. So it's sort of almost the other extreme where there's going to be lots of mechanics and technique that you want to practice and get good at, as opposed to sort of just the high level sort of understanding of what's going on that we did in the last chapter. Okay? All right, so that little preface out of the way, let me actually get to the introduction. So terminology, that's my goal here, so terminology. That doesn't look right, but whatever. So terminology. So the whole thing here is basically we want to start with this idea, like I said, it's sort of like a generalized counting. So let's say we have some number, but we don't know what that number is, right? So we have sort of a classic unknown number, right? So classic unknown number, we'll just say, give it a letter, right? So say we have some number. We don't know what it is, so we'll call it x. So when I say generalized counting, what I'm really saying is basically adding thing to itself, and in some sense multiplying it against itself, right? Because multiplication is sort of a shorthand for addition. But in this case, I'm going to multiply this unknown variable potentially against itself as opposed to some concrete number. So let's say I multiply x against itself. So multiply x by itself some number of times. I realize this again seems kind of abstract, just bear with me. We'll see where we're going in just a second here. So I'm multiplying it by itself some number of times. I'm going to give that a name, the number of times. I'm going to call that some n number of times, right? So if n is 3, then I'm doing x times x times x. I'm multiplying against itself 3 times. Then I'm going to take the result. So if I multiply it against itself n times, I get some, putting in quotes here because I'm kind of keeping track of what I have, some x to the n, right? Because I have x times x times x n times, so that's x to the power of n. And then take that, add it to itself some number of times, right? Generalized counting, where again, some number of times, I'll give this a name, so I'm going to call this some a. So if I add x to the n plus x to the n plus x to the n, etc., a times, I get a times x to the n. And this thing, this ax to the n, is sort of the most general term that we're going to be building up from in terms of polynomials. So this thing, so this ax to the n, is called a monomial. So, fun fact, this actually used to be called, and I'll just maybe put it in parentheses, you don't need to know this, but if it helps you remember, this actually used to be called mononomial. But they got rid of the extra no, right? Because it was M-O-N-O-N-O, M-I-A, right? So they got rid of the extra no to get monomial. Because really what we're doing here is we have mono for one, and nomial is actually from nomen, meaning name or term. So basically what I'm saying here, again, math people are not usually that clever with their naming. I have one thing, one term, where by term what I'm really talking about is things being added or subtracted together to one another. So this is sort of a building block of a polynomial. If I sort of put two monomials together, I get the next sort of very common name. So here, right, a and n are both sort of just generic letters, generic values, where n, this is, remember, a number, this is a whole number or 0, and a here is a real number. If you remember the is element of set of real numbers, right, from your sets bit a while back. So this is the monomial. If I add two monomials together, like I was saying a second ago, so if I still have ax to the n, but now I'm going to add another thing, so instead of a, I'll use, say, b, x to some other letter m. This is called a binomial, where, again, just like over here, we have mono for one, bi means two, so two terms, right? So two pieces, because I have it separated by the addition, okay? Less commonly, I'll just record it for the sake of posterity, I guess, here, but less commonly, we might also have ax to the n plus bx to the m plus cx to the k, maybe. This is called a trinomial. So basically, mono, one term, bi, two terms, tri, three terms. Again, not very surprising, right? So last but not least, we have what we would call a polynomial. Now there's sort of a couple things here that are important, which is why this gets a video, and I'm not just doing this as the first 5 minutes of some other video. So there's two pieces. I'm going to introduce one of them, and then I'm going to get some space, because I'm going to need some space. Well, actually might have enough room here, so let me do it over here. So combining or adding together, so I will say combining, but really what I mean is adding together. Any number of monomials is, well, the result is called a polynomial. Where again we had mono, one, bi, two, tri, three. Poly means many, so we have many names. Now this gives the impression, and that's why I'm going to underline this bit here, this gives the impression that many names should have many terms, right? If I have 5 terms, I would use a polynomial. If I have 1 term, I should call it a monomial. The reality is any number, including, say, 1 term, I could refer to as a polynomial, and that's sort of conventional. So even if I only have 1 term, it's very common you would still call it a polynomial. But by convention, we don't do that with any of the other terminology, which is weird. So for example, you could write ax to the n in this form where b is 0, and then say, oh, this is a binomial with some sort of stupid extra non-existent really term. You're not wrong, but if you're going to use a different name than for ax to the n other than monomial, it should be polynomial. So by convention, we will never call sort of a smaller one by a bigger term except polynomial. So you'll never call a monomial a binomial or a trinomial. That would be considered wrong by convention. In contrast, you can call any of these, and bigger ones, right, in more terms, you can call any of them polynomials. Okay? All right, so let me mark off some space. Now, I mentioned that you can have any number of these things as polynomials, and in fact, this gets a little more difficult. So I have to introduce sort of a notation that you may not be terribly familiar with, which is why I'm going to sort of go through it carefully here. So using my x to the n bit here, by convention, which for reasons that we'll actually get into probably in the next video, but if not, definitely by the video after, we tend to write polynomials in descending power order, right? So if you think probably from algebra 1, algebra 2, when you did like quadratics, you always did in that ax squared plus bx plus c, right? Where you had the highest power first and worked your way down. So this is something we do with all polynomials. So in particular, if we had some x to the n, the full polynomial that I would write would look like some x to the n is the biggest term, plus x to the n minus 1, whatever the next power down is, plus x to the n minus 2, whatever the next power down is, plus, and I'd keep going with this pattern until I got down to, note I'm leaving space for a reason here, say x squared, right, and then x, and then whatever the constant is, okay? But it's not just the powers of x, right? I need some coefficient in front of it. Now, here's the issue. I don't know what n is at all, right? N could be 5, right? Could be 10, 15, whatever. So n could be 5, 10, 20, right? I don't know what it is. So if I try to use the sort of standard alphabet, the way that we've been doing it when I did these other terms, right? I can be like, okay, well the first one, right, first letter in the alphabet, that's A, that's easy. Second one, second letter of the alphabet, I'm on a roll. Third one, third letter of the alphabet, too easy. But then I have this dot, dot, dot thing going on. And then I have x squared needs a coefficient. And the question is, what coefficient do I put there, right? I can't put just d, because that would suggest, right, that I have a, b, c, d, that like, what are the coefficients for all the stuff in there? Or are there just, am I assuming there's none in there? But I can't, because I don't know what n is, right? If n is 20, then this is x to the 17th I have a bunch of stuff in here before I get down to x squared, right? So if I knew what n was to start with, then I could maybe figure out what letter should go there. But the whole thing is I don't know what n is, right? So then I get sort of stuck trying to figure out what all these terms are. And actually it's even worse than that, because like, let's say that magically I could always know what n is. What happens if n equals, say, 500? Right? I don't have that many letters. I would be going through the alphabet some, like, whatever it is, almost 20 times, right? 19 and change. So I would have to either have like a coefficient that's like a 20-letter long thing to make them all different, or I need to have a different plan, okay? And it turns out there's a much, much better way of doing this. This is where we get into subscript notation. So a lot of you are probably perfectly familiar with this, but just to make sure we're all on the same page. So the way that we do this with subscripts is we're just going to use one letter, and we're going to use the subscript to sort of mark that they are different from one another. So I'm going to have the same sort of setup where I'm going to have some x to the n plus x to the n minus 1 plus x to the n minus 2 plus sort of dot 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 plus x squared plus x plus some constant. The letter I'm going to choose, I'm going to go with A, just because, again, it's the first letter. Why not? There's no reason I need to use A. I could use any other one, but that's sort of the conventional one to use. That's what I'm going to stick with. So I'm going to use A, but I'm not going to do A, B, C, because we just talked about how that didn't work. Instead, I'm going to have an A with a subscript that matches the coefficient, matches the power, excuse me. And that's by design. So I'm going to have AN for x to the n. I'm going to have A n minus 1 for x to the n minus 1. I'm going to have a n minus 2 for x to the minus 2. And matching them like this, I'm doing this on purpose because that tells me immediately what the subscript should be for any of these. Because if I want to know, for example, what's in front of x squared, it's still an a, and it's with a subscript that matches the power. So this one's a2. All right? Here the power is 1, so I get a1. Here it's a little weirder because I don't have, right, the subscript, or sorry, the x term, but I kind of do, right? Because really what's happening here is I have some x to the 0, right? So this is going to be a0, where really I'm just not writing the x to the 0 normally. Usually, maybe I'll erase it here for now. Usually we just don't write that because x to the 0 is 1. Usually, which we'll get into later, but we can assume for right now x to the 0 is 1. So usually we just have an a sub 0 at the end, and that's how we say this. A sub n minus 1, a sub 1, a sub 0, right? So that's the subscript shorthand. And really it's because there's a x to the 0 floating there that we're not writing because it doesn't actually change anything, okay? And the nice thing about this is that the subscript can be whatever it is, right? If n is 500, I'm just doing A500, A499, A498, A497, A496, dot, 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 right? Just keep going. I don't need to worry about if I have that many letters, okay? So this is the standard form of a polynomial. Okay? Okay. I was going to do this as the second video. That's what I mentioned earlier, sort of the notation bit, but honestly, this isn't so bad, so I'm just going to keep going. All right, so there are a few things that I want to point out here. So this is the standard form. This is how a general, like we don't know anything. This is the most generalized version, right? Normally, if we have a polynomial, we'd actually write out numbers. So we'd have like 5x to the 5th plus 3x to the third plus whatever, right? I mentioned that by convention we write it from the highest power to the lowest power. I should also mention that you never want to assume someone is sort of going along with convention. So even though when you do your work, you should write it from highest to lowest power, for reasons I'll get into in a second, when you first look at what somebody has given you, never assume that's the case. Look through it and reorder it from highest to lowest power, because if you just assume that the first one is the highest power, you may make some pretty important mistakes, okay? When we have it written down, then this first thing here becomes very, very important, okay? So the term with the highest or largest power is, I should write this sort of better, is called the leading term. And this is because the leading term actually will tell us a lot, all on its own, about a given polynomial. And in fact, a polynomial will, and I'm going to put this in quotes here, eventually, it's one of those not very precise terms, which I'll explain in a second, will eventually behave, another not precise term, like the monomial that is its leading term. I messed that up. Leading term. Okay. So what do I mean by that? So eventually and behave, what do these terms mean? So I will right off the bat tell you that these are things that in order to make truly precise what we mean by that, we need limits, which we won't cover until calculus. So that's not a thing that we're going to cover in this class. So we're going to sort of have to make it still kind of generally hand-wavy. So what we basically mean by that is that when x gets big enough after some point that we don't really know when that happens, but when we think about x getting really, really big, either positive or negative, whichever direction, eventually, when x is big enough, it'll behave like, what that means is that the polynomial, even though it has all these extra terms, all those extra terms, when x is big enough, eventually, really don't do anything. All of them sort of fade to the background, and if you were to just look at the monomial, the leading term all by itself and ignore all the other pieces, you get roughly the same result. So if the monomial up here gets really big as x gets really big positively, right? So if that thing gets really positive and large as x gets positive and large, then eventually, meaning if you pick large enough x in the positive direction, the whole polynomial will do that same thing, regardless of what these other things are or doing, no matter how big the other coefficients are, okay? So when we talk about eventually, that's the part that you sort of need a lot more rigorous tools to be able to talk about. So we can't really specify when that happens. We just know that there is some big enough x value, positive or negative, where it will start looking like just this term, sort of graphically, okay? Also in terms of terminology, so we have leading term, which is important because of this bit, and the coefficient of the leading term is called the leading coefficient. Again, not very creative when it comes to naming. So Again, these are things where they are used often in like other classes and stuff. So these are terms you want to know when the professor says it, you want to know what they're referring to. But the leading coefficient itself has some impact. More often than not, we really care about the leading term, the whole thing, everything. But occasionally we just care about the number in front of the power of x. When we're talking about whether this thing's sort of going negative or positive, for example, that'll have a big impact whether that leading coefficient is positive or negative, okay? And that's something we'll get into a little later. And finally, for terminology, the degree of the polynomial. This is another terminology. Nomial is the power of the leading term. Or another way of saying this, which is maybe a more common way, is that the degree of a polynomial is equal to the highest degree term in that polynomial. Okay? So if you had the polynomial, sort of a little out of board space here, sorry. So let me maybe write an example up here at the top. So if I had an example that looked like 3x squared plus 2x to the 1 minus 16x to the 5th plus 7, right? So here, again, by convention, I would write it from highest power down, but you never want to assume that. So the first thing I'd do is look through this and rewrite it in that sort of standard form. I can still skip powers that aren't written. I could write them as well by putting a 0 in front, but I'm not gonna. So this thing is really negative 16x to the 5th plus 3x squared plus 2x plus 7, where now the leading term is negative 16x to the 5th. The leading coefficient is negative 16, and the degree is 5, right? So the leading term is the highest power term, which was this one, negative 16x to the 5th, right? And be careful, because if you didn't notice that this was minus 16, you might have written it's just 16x to the 5th, and that's not right, right? Because you need to put it in front, which means it needs a negative. So the leading term is negative 16x to the 5th. The leading coefficient is the coefficient attached to like that leading term, so it's negative 16. And the degree of the polynomial is the highest degree term, which is also the leading term, the degree of that term. So it's x to the 5th, so this is the 5th power, right? It's the power of in that term. Okay? All right. So this is sort of the terminology and general notation for polynomials. I'll point out, again, in case it wasn't clear, they're made up of all these monomials, right? So we might have binomial, trinomial, but polynomials just mean we have some number of terms. Could be 1, could be 2, could be 3, could be 500, right? It's a good idea, whatever you're handed, to write it in the conventional form, the highest power to lowest power, because that gives you your leading term, which is leading because it's leading the list of terms. It's in the front in this way of writing. The leading coefficient is the coefficient of the leading term, hence the name. Degree is the power of the leading term, right? Everything's coming from that first thing, which is why it's nice to have it right up front. All of the powers have to be whole positive numbers or 0. So I can't have any fractional powers, I can't have any negative powers, it has to be whole powers or 0. And the coefficients can be any number of the real numbers. So I could even have, for example, 0, although that would give you sort of a flat line, y equals 0, which we don't usually worry about, but it is technically a polynomial. More often than not, right, we would have non-zero stuff there. And whether it can be 0 or not is actually a sort of recurring theme in certain definitions. So be sort of a little aware of whether or not your leading coefficient here can be 0 or not. Here it can be, other places it won't be, okay? We have this subscript method, and then we have our terminology. Okay, so that is that.